Hello, everybody, and welcome back to the first math and physics podcast episode in a very long time. Unfortunately, Rehan was unable to attend this in-person interview style conversation because he's still in India. Alas, this was a really great episode. Our guest today, his name is Jacob Taylor. He did his undergrad at the University of Toronto in the Astronomy and Physics Specialist program, the same program that I just graduated from, and he's currently still at the University of Toronto doing his PhD in astrophysics. He's got 1 year left, and so at the end of the academic year in 2024, he will have his PhD. He's done some really interesting work in radio astronomy, but even more interesting is now he works in the field of adaptive optics. And Jacob and I have actually been working together for a year now. I have been doing my undergraduate research, which is basically a subset of his doctoral research. So we've been working together and we've been doing some really interesting stuff that we talk about during this episode. Just a little warning. Rehan and I, we did an episode called just talking about adaptive optics and CFD, which is computational fluid dynamics. And in that episode, I do a huge introduction on the basic ideas about adaptive optics. And so you might want to go listen to that episode before you listen to this one. This is more of an in-depth conversation, more specific to the things we're actually working on right now. So I recommend you go and watch that before. If you're brave, then go ahead and keep listening. This is a really great episode. So yeah, enjoy. It's the language of the universe.
But I don't understand it.
Weekend getaway at the cottage, and then
basically, yeah.
Now you're back here and back in Toronto.
Yeah, now I'm back, ready to do more research, stuff like that.
Yeah. So we were actually writing a paper.
Yeah.
And the summer research program ended, and then I got lazy, and then I didn't work on it since, by the way.
Yeah, I've been gone for a couple weeks.
Yeah, you've been
gone. That's kind of the main priority, I think, because I have to graduate, and I don't need a certain number of papers, but it definitely helps if it's already. Yeah, I think if you do theory and other stuff like that, theoretical physics, typically you need, they say 3 papers stapled together is kind of your thesis. Instrumentation and other sort of things, it doesn't always work out that way, because getting 3 sort of first authored papers in instrumentation is pretty hard, because it takes several years to build the instrument.
Yeah.
And instrumentalists just, I don't know, papers aren't necessarily the number one way we show our
for sure,
our progress,
because it feels weird, you build an instrument and then you write a paper about it,
Sometimes with the instrument papers, it's just to kind of tell. There's different kinds of instrument papers. The big ones are the ones that just tell the other astronomers, this is the instrument that exists, this is what it can do. But those, oftentimes your instrument will be operational for a year or so, something like that. And then you will write some sort of big paper once you have enough data to show how it performs in different circumstances, and show that you've met your goals and things like that. Then you sort of write this big paper, and that's usually written by the PI or someone who's been really involved with the project.
I think that's kind of the advantage of working in instrumentation, is that you get first dibs on all the data.
Yes,
and
it can be. There's a certain group of people who are kind of in between data and instrument, and then when the instrument actually gets data, they get first dibs. I know some people like that. None of my instruments have produced great data yet, so.
So what would you consider your instruments?
The main thing that we work on is the MAPS project, which is the MMTO Adaptive Exoplanet Characterization System. which is essentially the adaptive optics system for the MMT Observatory in Arizona. That's basically the project. That's the sort of biggest ticket project that we work on. Although that project is being led by the team in Arizona. So it's not necessarily like our project, but it's the biggest project that we work on. I think technically we're commissioned by the University of Arizona for specifically the infrared camera for the infrared pyramid wavefront sensor, and also the calibration. Those are like the ones that we're sort of written in to do in Toronto. But they operate like they're much closer to the actual telescope, so they have obviously a bigger role in terms of like the facilities. They're responsible for the adaptive secondary mirror and most of the sort of larger components.
Yeah, it seems like at Toronto, where like our responsibilities are very specific, and like what other kind of like instruments are there up at the MMTO?
At MMT, I don't know so much about the instruments that are not AO related. They have the main thing they do is just sort of more standard astronomy stuff. Like they have surveys that they work on. The telescope is it operates every night of the year. Every night they have a full-time operation with, I think there's like 2 big surveys that they do. I don't know much about the specifics of like what the data looks like at all. I know there's like some spectroscopy, but it's not AO fed.
And so they don't. Yeah, okay, yeah. They don't run with the.
It's just big telescope, lots of photons.
Do they keep the secondary up there and just don't operate with it?
No, they have 3. They have 3 different secondary mirrors on the telescope.
Okay. What's the third one?
They have like the F15 is the adaptive secondary, and then they have a wide field, and then I think they have like a regular one. The wide field one is like really big. I've seen it. It's like, I don't know much about the specifications, but I mean, sort of visually, it's just a really big mirror that's quite close to the telescope.
Yeah.
So you've seen when you're at MMT, like the F15 is the adaptive secondary mirror is pretty far up there. It's not super close to the telescope.
That one's like a meter in diameter, right?
65 centimeters.
Oh, okay.
Yeah. It's about 10% the size, the width of the full mirror. And then
True, I guess I knew that.
but then the wide field imaging one is I don't know exactly, but it's big. Like, but it's not adaptable. It's just like a piece of glass. And they switch routinely between them. If you look at like the schedule, you can see which one they have on. And so I think that's fairly unique for telescopes. I haven't heard so much about telescopes switching out their secondary mirrors so much. A lot of other telescopes, basically, they have the instruments at a different focus. So that to change instruments, they don't have to actually change much about the telescope. They just rotate a mirror.
Yeah. So do you know like what the MMT is good for? Well, there's a lot of like different instruments are good for different purposes, and MMT was built a while ago, so maybe there are new instruments that just do the same job but better.
Oh, I mean, for sure. I don't think that in modern times, the MMT is necessarily like the world's best telescope.
Yeah.
One of the big things with telescopes is just that the bigger they are, the more photons they collect. People often talk about telescopes as essentially just big light buckets.
Yeah.
And so, I mean, the MMT is 6.5 meters, which is big, but it's not the biggest. And so if your goal is to just take a photo of like the faintest thing, I mean, it's the same size as James Webb. So James Webb is in a lot of ways strictly better.
Yeah.
And
especially because it's in space.
It's in space.
Yeah.
So there's a lot of the issues that you have from the ground you just don't have in space. That's why I put.
But that also comes along with its own bag of
exactly.
Its own bag of tricks.
So yeah, I mean, the MMT when it was built, it was amazing, and now it's still an amazing telescope. It still does a lot of impactful science. It's been pretty productive. But the stuff we're working on is basically revitalizing the EO system that was there. It was originally built in, I think, the early 2000s. It was the first adaptive secondary mirror ever built. And yeah, it came online, I think some of the early papers were like 2002, 2004. And then it was operational until 2017. It was officially retired. And then we're basically refurbishing it, giving it new life, and, you know, focusing on types of science that are more difficult to do in space.
Yeah.
Obviously, you know, there's not necessarily a huge point to build a fleet of ground-based telescopes that can do the same thing as James Webb.
Yeah.
The advantage of being on the ground is that you can build much more complicated instruments that you can't put in space. You can't just, you know, fly the world's most complicated instrument in space without, you know, billions of dollars of development.
Yeah.
Whereas for, you know, relatively cheaply compared to space-based costs, you can build ground-based telescopes that are, you know, have very comparable capabilities.
What do you think about, I don't know why this thought just came into my head, but, you know, building a telescope on the moon, there's no atmosphere.
Well, there's actually proposals to build radio telescopes on the moon.
Yeah. Oh, as like
on the far side of the
as
moon.
like an interferometer with the Earth.
No, just because there's no radio frequency interference.
Oh, okay.
Because the whole moon, if you put it on the far side of the moon, it blocks it. So different types of radio telescopes have problems where basically one of the main problems is that, you know, we're emitting a lot of radio interference. That's how we communicate all around the globe.
Yeah.
Whether it's your cell phones or television signals, radio signals, airplanes. I did some work in radio and on radio frequency interference. And basically, if you go to the far side of the moon, you have a big crater, and there's, you know, it's a much more hospitable environment for radio telescopes.
And easier to build than pretty much any other telescope.
Well, we have radio telescopes, especially in like low frequency radio telescopes. Like, they're just dipoles. I mean, they're just like pieces of metal. They're macroscopic.
I built one at the summer school. That was hilarious. I had no idea that it was that easy.
Yeah, I mean, it's just a piece of wire.
Yeah.
Right? I mean, look at your car antenna. You know, it's not like when you compare that to like the way optical telescopes are built.
Is that like a monopole, the car antenna?
Oh, I don't know.
Because
there's no like car antennas. I mean, television antennas are basically just pieces of metal that are such a size that they resonate with the wavelength of the light being emitted. Yeah. So that's why you'll see like the Christmas trees. I think they talk about them, where if you look on like a building, you'll see basically it's a big piece of metal with different metal rods that are different lengths. Yeah. And those sort of correspond to different frequencies because of the wavelength of light at different frequencies. Yeah. That resonates in that. Yeah. I think in the summer school you guys would have done something similar.
Yeah. Like I never really thought about, you know, what an antenna actually does until this summer school. And the way they explained it, I mean, it's actually quite simple. You know, you take half a wavelength of what you're trying to observe, and that's how you get the maximum polarization in the rod. Because essentially you're just trying to push electrons back and forth.
It's just a sloshing of electrons with a wave.
So if you want to create the most amount of force, you go, okay, I want the most negative part of the electric field on one side and the most positive one to get the highest gradient, and then you're just sloshing them back and forth, and then you're just recording how they move.
Yeah, and you get a lot more information in radio too, because you get the full complex electric field. So you don't have to, like in optical astronomy, we have to use the photoelectric effect. Yeah. To have photons that excite electrons, and you're measuring the intensity, and we go to a lot of trouble in adaptive optics to measure the phase of light. That's like what a wavefront sensor is, a lot of it. And we're trying to measure and correct for the phase of the light. When in radio astronomy, they just get it for free. Yeah. Because they're measuring the electric field itself.
Yeah, and there was a talk about like radio astronomy during that summer school, and it was by Keith, and he was talking about how when you observe the electromagnetic fields on Earth, you're recording the Fourier transform of your source, and I thought that was incredibly interesting.
Yeah, there's a lot of like Fourier stuff that goes into radio astronomy. I mean, like you can kind of think of like spectrometers and optical as sort of like physical Fourier transformers.
Yeah.
That's kind of how I've always thought about them. And that's the nice thing about radio is they sort of get it for free. Like you get they literally just do a Fourier transform or some Fourier transform analog to actually record the spectrum.
Yeah. One thing I don't quite understand is why can't we just adapt the instruments to, like in radio, we're able to get the phase of the photons that come in. Okay, whatever. Why can't we just change the instruments to do the same thing at shorter wavelengths? Why do we have to develop something completely different?
Oh, it's just different physics regimes. I mean, radio, you're basically entirely in the wave theory of light. Yeah. And then in visible and stuff like that, we're kind of in like the sort of quantum, particle wave duality thing.
Yeah.
It's just the physics operate differently in different regimes. That's kind of the fundamental reason why, if I understand it. And so there's just not a better way. The photoelectric effect is kind of just the sort of standard way. And then there's a weird regime in microwave where they use like bolometers, which use like, I did some work on transition edge sensors, like very briefly.
So what are those?
Transition edge sensors is essentially when things get like super cold, there is like a regime where small changes in temperature result in like large changes in, I would say, voltage, something measurable. And so someone describes me basically as like, imagine if you could like put your hands up at the sky and feel like the temperature of Mars.
Yeah.
Basically they use like the temperature change from something like Mars to to basically change the temperature of something like a superconductor very slightly, and it changes the resistance of the sensor, and that's what they're actually measuring. And that's how they do a lot of the CMB science. They get small temperature changes that way. That's like what I think the South Pole Telescope works on. So I did a brief stint as a transition edge sensor researcher one summer. That was my summer project in grad school.
So just as you were starting grad school?
Yeah, right as I was starting. It was right in the pandemic, so it was a very short-lived experience.
How did you get into that? Like, did someone just tell you like, oh, we need someone to work on this?
Well, there was actually a new professor at the university, and right before, this was in 2020, so really early 2020, I had to decide what I wanted to do for my summer. It was my first year of grad school. For the main school year, I was working with Suresh, our current supervisor, working on what I'm currently working on. At the time, I didn't know that I was going to actually continue to work on that for a while, so I had to find a summer project to work on. And I thought I was going to go to California for the summer.
Oh, cool.
Because the professor that was working on this, she had a team in California that was where she was working on before she came to UT. And so I was going to go, I was like, oh yeah, I'll go to California and I'll work on some of the instruments there. And then that didn't happen because instead I was at home in my house trying to learn about transition edge sensors from my bedroom.
How was that? Did you find it interesting at least?
It was a little bit interesting. That was a really different time especially for people who were working on instruments. Like I didn't have a lab. I didn't have anywhere to go during the day, like a lot of other people. And because most of my work was sort of in person, in a lab, I was, basically without work. That summer I was kind of I took up like carpentry.
Well, just in your garage.
Yeah, basically.
Cool.
Yeah, with my roommate, we were like, what if we just started building stuff around the house?
Did you take like a course online or something?
No, I just went to Home Depot every day.
Oh, just winging it.
Because we could Home Depot was open.
Yeah. This was in Toronto?
Yeah, it was in Toronto.
Okay.
Yeah, it was in the East End, and basically we had this house that I was living with my cousin at the time, and that first summer we were just so bored that we were like,
Did you make a chair or a table or something?
I ended up making like a ramp I don't know
For
why.
what?
My backyard.
But like
And then
to roll
I just thought it looked
stuff.
nice.
Okay.
Yeah. And then he made a pull-up bar that he like never used.
Nice.
He was like, "What if I made a pull-up bar for super tall people?" So it was like a 10-foot pull-up bar.
Nice.
I don't know. We made some other stuff, but some flower beds.
Like a freestanding pull-up bar?
Yeah,
Or like
like
something that you would attach to.
no, like a
Oh.
10-foot sort of like
Nice.
wooden 2x4
Yeah.
pull-up bar in
Yeah,
our
cool.
backyard. Our neighbors thought we were crazy.
I mean, it's something to do.
Yeah,
Yeah,
I
it's-
mean it was pretty. I don't know if it was boring. It was more just like there's only so much you can do
Mhm.
when you're trying to learn like
Yeah.
lab work from
Yeah.
afar. I think some other people made a lot more progress, but I think generally like the professors kind of understood that we weren't going to do much.
Yeah. Did you know about AO at the time?
Yeah, that was after I'd done like I did an 8-month project, my initial
Oh,
project with
yeah.
Suresh. When I first started grad school, I was working. Well, in undergrad, I was working on radio astronomy with Keith, one of the professors here.
Oh, yeah.
I was working with him for two or 3 years. I started in second year undergraduate.
Damn.
I
I didn't
actually
do research in second year. I thought I wasn't ready.
Well,
Well, I thought I was ready, but they said no. So
I was on Facebook, and there was like a Facebook group for, I don't know, maybe this is probably one of the things that changed a lot since you were in school, since when I was in school.
Mhm.
There was like a 5-year period where Facebook went really downhill.
yeah.
But back in 2015, when I started undergrad, Facebook was still kind of a big thing. And so when you went to university, you would like join your year's like Facebook group.
They still do that.
They still do that?
Yeah, they
Yeah.
did that for my year. Yeah.
Okay. And it was like a big thing. People would post like these long bios about themselves. Do they still do that?
Yeah.
Like,
Yeah. I think it's more scarce now because Facebook is a little bit on the fringes.
I remember it being like really cringy.
Yeah.
but-
Yeah. I don't think I did it.
No, me neither. But on that kind of, that was where I found out how to, my first research thing. So like I started second year, and I don't know why I had the motivation to do research. I just done a summer as like an intern at like a computer. It was like a military contractor thing, and they did like co-op students.
Yeah.
So I did a co-op, and I was really confident. I was like, yeah, I'm gonna do research. I
Yeah.
had no idea what I was doing.
Yeah.
And so on Facebook, they were looking for like research assistants, and this happened to be the year that they were like building CHIME, which is the Canadian Hydrogen Intensity Mapping Experiment, which is like probably the biggest Canadian radio project.
Yeah.
At the
gonna be
time,
the
it wasn't. At the time, it didn't exist. So, you know, this was before they were like on the cover of Nature and stuff.
Yeah. They're about to be the second biggest.
Cord?
Yeah. Right beside it, they're gonna build the
Cord, right?
Cord, which
Yeah,
is
yeah.
64
I don't know.
dishes. I don't know.
Something like that.
Yeah.
So basically I remember talking to like Keith, I was in second year, and they posted this thing online, and he basically needed a bunch of students to assemble graphics cards and to assemble computers nodes.
Were you qualified for that?
No, not at all.
Okay.
Not even close. So they put us like, I remember he didn't know what he was getting. Like some guy, I don't know how he found out about this program, but he signed up for it because he was in desperate need of students. We all got put in a room. I went to like a super like sketchy interview with some random third year student in computer science.
Yeah.
I went into Bain, and it was just like, hey, what do you know about radio astronomy? He was not affiliated with the astronomy department. It was just some guy that
Yeah.
was running this program as like a co-curricular, I guess. And then I was like, yeah, I can do radio stuff. He was like, okay. And then put me in a room with a bunch of other students, and they were like, do you want to do software or do you want to do hardware? I was like, I guess I want to do software.
Oh, so you got the option to do whatever you want, pretty much.
Yeah, and then I don't know. There was like probably 15 students that were in this program, and like I think after like a few weeks there was like 3. I don't know.
So this was a summer program.
No, this was like in the middle of the
Oh.
school year.
Oh.
Yeah, and it was volunteer. Like it was just
Oh.
I don't know.
So this was after your second year.
No, this was like October of my second year.
Really?
Yeah.
Wow.
Yeah.
So you knew like
I
nothing,
knew nothing.
pretty much.
I knew nothing.
Yeah.
Like seriously nothing. And I just was pretty good at programming.
That's brave.
And so basically, literally what happened was I just started showing up to meetings.
Yeah.
You know, like I found out, as soon as I found out of the project, I just started showing up to meetings and pretending like I knew what I was talking about. And that went on for like a year.
Did you have to talk
In the
in
meetings?
the meetings?
Not much.
Okay.
It was just like, I was just learning. It was like, at the time, it was a small thing. Like Chime was, it wasn't built yet. Like it was I think it had just been kind of built around that time. But they were building the computer behind it. And so at that time, it was just kind of like, 2 or 3 people in the room. And I was just like some random undergrad who showed up to the meetings.
Wow. So it was like pioneered at U of T, basically, at least the beginning of it.
No, this was like the computer, like
Oh, okay.
Toronto's big, what do you call it? Contribution was what's called the X engine. So it's like the radio correlator. Together it goes with an F engine, which is like the Fourier transform part of the radio pipeline, and that's made in McGill.
Okay.
In Montreal. So it was a collaboration between University of BC, UBC, McGill, Toronto at the time, and then there's been a lot of professors who have gone to a bunch of other places in the U.S. and stuff now. But at that time, those were like the 3 big contributors. Whereas like in BC, they were actually building the telescope. It's there, it's in BC.
Yeah.
And then at McGill, they were building the F engine, and then at Toronto they were building the X engine. And they had to actually assemble the X engine, which is 256 computers, each with 2 graphics cards that had to be split, and had to be they had to put manual cooling on them, liquid cooling.
Yeah.
So all of the graphics cards were disassembled in the basement.
Damn.
And they were trying to they had students who were doing that. It was just so much labor. They had a lot of students, like summer students, and
Yeah.
there was a bunch of different people who were working on that. And then I did not work on that. I was working on software.
Okay.
Which
if you would have picked hardware, you would have been
if I was
disassembling cards.
No,
all day.
seriously, if I'd picked hardware, I would be disassembling. Yeah, that's exactly right.
That's funny.
But I picked software, so I don't know. Then I just I just kept showing up. That was really what happened. And then I got into summer programs and stuff because I had a reference letter, from Keith, I guess. He was my professor that year as well.
Yeah. So first you started off doing a project in AO for grad school.
So I did this radio for 2 more years.
And then I
got into grad school. Yeah.
And then you worked with Keith after that.
No. So when I got into grad school, that's when Keith actually was on sabbatical.
Oh, okay.
The way I got into AO was basically that the professor I was currently working with went on sabbatical. He had
I had the timeline reversed.
Yeah. He had some kids, and he had a bunch of other stuff in his life, like kids and marriage and all that kind of stuff, I think. And so he was gone for at least a full calendar year. Could have been longer, I'm not sure. And so at that point I was just like, okay, maybe I'm going to work on AO.
So how'd you find out about it?
Well, I got to grad school and I had to do something.
Yeah.
In our program, you don't pick a project before you come. You show up on the day, and it was September, just like you next week.
Yeah.
That was me. I kind of showed up and I was like, okay, I need to actually, work on something while I'm here.
Yeah.
They have a program called, here it's called AST 1501, AST 1500, which are 2 courses. They're courses. They're just research projects. It's basically your full-time job. It's a sort of a structured full-time research job is how I would classify it, with courses on the side. That's kind of how it was. And so you get to go and basically shop around for a project. I had a meeting with Suresh, and I said to him, I want to work on something that's sort of more high performance computing esque. And he told me about AO, told me about their adaptive optics bench in the basement and what they needed to do. And
Be careful with the chair, by the way.
That was history. Yeah.
Well, so you started working on AO. What kind of projects were you doing in the beginning?
Well, the first thing, what I was kind of brought on to do was the software. They had an AO bench that was relatively new, and the purpose of the bench was to basically test.
So it was there when you got there.
Yeah, it was there when I got there. Not in the current state it's in right now. It was very different. It was only optical. Now it's sort of optical infrared, which means we had to buy like all new optics for it. And it was run entirely in MATLAB with like a little bit of Python. And basically it was just really slow. I think they were going like max 100 hertz kind of stuff.
Yeah. So what's the issue with running it at 100 hertz?
Well, there isn't necessarily an issue with it. The main thing is that the camera that we're testing runs at like 1.5 kilohertz. And this was the camera for the MAPS project for MMT. So the camera was being developed. At the time I joined, there was a student, a grad student who was a year ahead of me, and his main project was this camera. He was like an engineering type student. I think he did some astronomy as well. And his full-time thing was getting this really fancy camera operational. And that camera had the capability to go, it was spec'd for 1 kilohertz, which is like 1,000 images per second, or 1,000 FPS.
Yeah.
And I had done a lot of stuff in like C and sort of more high performance computing and radio. And I was kind of interested in writing something that was what's called the real-time controller, or the RTC. I was basically really interested in updating it. What they had was like super basic, I would say, and doesn't scale super well. So yeah, that was my main project. I mean, that's what I was working on.
So there was the deformable mirror and the wavefront sensor, and essentially the job of the RTC is just to, in real time measure the wavefront and then control the mirror.
Yeah, it's basically the real-time controller is the missing link. It's what allows your measurement and your correction device to communicate with each other. And I think that Suresh and everyone who was working on the AO team kind of knew that it needed to be more, the software needed to be better if for like long-term success of the variety of projects that we're going to work on. But yeah, that's basically what the RTC does. The sort of the sky's the limit with the RTC. I mean, it like they can get really, really complicated. And
so what makes it complicated though? In my head, it's just like you have a signal and you have a input output,
Speed, the actual, what you're right in saying is like the math is not super complicated, relative to like, astronomy on whole. There's like a lot of complicated math and complicated control systems, but the main thing is speed, because you have to go fast enough to sort of correct for the atmospheric turbulence. And the atmosphere is only stable on sort of like the 2 millisecond to 5 millisecond time scale, which means that you have to fully correct for the atmosphere faster than that. And if you want to do like really well, you have to go substantially faster than that, depending on your scientific goals, etc. And that essentially, you have a matrix multiply that you have to do. A lot of high performance computing, I think, ends up being like, how fast can you do matrix multiplies? So you have to do matrix multiplies, 1,000 times a second, and the more actuators you have on the mirror, the more ways in which you can correct for atmosphere, you have more numbers to multiply. So at some point you hit the limit of how fast your computer can do that. And then if you want to go faster, you can like implement GPU ways of doing matrix multiplies, etc. So really, for big modern systems where you have a lot of actuators and you have images being taken very fast and fairly complex ways of taking those images, your real-time controller can get quite complex. There's also ways of extending the mathematics beyond like the most simple case, which is just a single matrix multiply. A lot of the modern control mechanisms tend to have more than one matrix multiply, or neural networks, things like that.
Yeah.
And yeah, basically you need a pretty efficient software to actually get it done in time.
Yeah.
That's one of the major complexities. The other complexities are just kind of like algorithm based. So calibration schemes, different ways in which you can control the mirror, doing different modal bases, and oftentimes a lot of the hardware you're working with is not like off-the-shelf hardware. It's like custom, like for instance, an adaptive secondary mirror is like complete custom job.
Yeah.
So to control that efficiently is very difficult.
There's nobody else.
No, there's the
can tell you what to do.
It's a one-of-one piece of hardware, and
Yeah.
anytime you work with like one-of-one piece of hardware, the control software could be quite complex.
Yeah. This kind of work sounds more like the job of a computer scientist as opposed to an astrophysicist.
Yeah, I mean, it's software engineering is like a big part of what I do. The astronomy stuff is it's a little hard to understand when you compare it to like the traditional astronomer approach. But the reality is that adaptive optics is a fundamental technology in the space of astronomy, ground-based astronomy, and it's becoming more so as we build bigger telescopes. The potential benefit of having a good adaptive optics system on a bigger telescope, it's non-linear in terms of its improvement. Like it's not just like I build twice as big a telescope and I use adaptive optics, I get twice as good.
Yeah.
So with the new telescopes that they're building are these like pretty large sort of 30-meter class telescopes that are being constructed by the world's governments. They're going to be equipped basically they're universally equipped with large, complicated adaptive optics systems. They were designed sort of from the ground up with adaptive optics in mind. And there's not really like a group of people who aren't astronomers who benefit from this work in adaptive optics. It's like, it's used in a few different fields. Adaptive optics is used in like, medical stuff.
Yeah.
Other types of imaging, but the challenges that are presented by astronomers are unique in such a way that you need to make progress in ways, both algorithmically in the software, also in the hardware, that you don't need to make for other fields.
Like building 1,000 actuator adaptive secondary.
Yeah, exactly.
It's ridiculous. I mean, nobody else would ever have a use for that.
Yeah, exactly. No one is gonna. Yeah, adaptive secondary mirror is a great example. I mean, like there are 4 telescopes. The amount of actuators you have is insanely high. There's not any other that I know of reasons you would need that high level of actuator density. And so really astronomy in many ways is like sort of the hardest test case for this technology. And so if it's not astronomy, like what is it? That's really the question.
Yeah.
Because yes, it's like very much focused in engineering, but you're solving questions that are based off of the way that astronomy works, like the way the atmosphere works, the way that we're taking images of stars, and you're facilitating the people that do that. And there's not like a group of engineers that are sitting out there that are just like, we're adaptive optics engineers who are going to like solve this problem.
Yeah, I find it great how different fields collide in trying to solve this problem, because you need to know about the atmosphere in order to properly design your systems. And so now all of a sudden you're talking to atmospheric physicists who know things like the R0 parameter and like the physics behind what you're trying to correct. Whereas, as astronomers, we didn't even want to get into this mess into the first place, right? We wish the atmosphere wasn't even there. Now all of a sudden we're, looking into, how it actually works, and we're learning things about the Earth as a result.
Yeah, I mean, it's there's some quote from like Isaac Newton about atmospheric turbulence. Like people have been noticing and thinking about atmospheric turbulence for a long time, and how to correct it. And so in some sense, it's, it's like instrumentation generally is like this weird multidisciplinary combination of things.
He was talking about that regarding astronomical observation, like correcting the atmosphere.
Yeah, I mean, well, like people, especially people back in the day, I mean, they're really interested in the stars for like hundreds of thousands of years. I mean, it's one of the things people have been talking about forever.
You can tell though in Newton's time the effect of the atmosphere.
I don't think they understood it the way we understand it today.
Yeah, I mean, of course.
But I think the whole idea of speckles is very old.
Yeah.
Speckles is being basically the way in which when the starlight passes through the atmosphere and you sort of see it, it kind of forms these speckles.
Mm-hmm.
And you can see them very clearly through telescope, through a telescope. And those speckles are, what we consider atmospheric turbulence. It performs this sort of specklish pattern.
Yeah.
And yeah, I think people have known about those for a long time. I don't exactly know when they figured out that it was like the physics behind it and why exactly it happened.
The first thought was probably that, that's just what the star is giving us. Right?
I don't know actually. I mean, the earliest quote I know of, I think, is from Isaac Newton about actually thinking about turbulence. But yeah, I don't know what people would have thought about.
I mean, that's a complex thought to think about how the air is affecting the light that reaches your eyes.
Yeah, I mean, it's the same thing as it's kind of like looking through a swimming pool.
Yeah.
It's a similar idea. Yeah.
Yeah. I guess once you realize that fluids behave in a similar way.
I don't know how old the idea of air being a fluid is.
Me neither. We're not the right people to ask. But the one thing that I found really cool, and this is maybe related in some way, but when we were sitting in the lab downstairs putting shapes on the mirror to calculate an interaction matrix, and these are all big words, but that's not the point. The point is that we were altering the phase, or the path differences of light, and it looked like changing the shape of water almost. It looked like fluid in that sense.
I mean, it's the mirror is very I don't know what the word is. It's very bendy. Right?
Yeah,
it's kind of like
it has to replicate
a thin surface, right?
It has to replicate kind of the effect of the atmosphere, which is very fluid in a sense.
Yeah, I mean, it's basically just it has to be deformable.
Yeah,
that's the idea, right?
Yeah,
it has to be able to correct for an arbitrary path length shape.
Mm-hmm.
But yeah, I mean, it is interesting, like how these ideas of like phase in light and how they work in other contexts.
Yeah, and so then the idea of how do we measure the effect of the atmosphere.
Yeah, the measuring stuff has been around for a while, and it's actually it's a super interesting side of adaptive optics. Is basically it's called wavefront sensing.
Yeah.
And it goes back many years. I think a lot of it was pioneered by the military. I know that in I want to say the 70s era, the U.S. military was responsible for a lot of the advancements in adaptive optics. It was sort of first, I think, theorized for the fundamental concept. I think goes back to the early 50s. But then I think after that there was a big era where it was really the U.S. military was sort of trying to advance the technology. There's still to this day a lot of military implications related to taking images through the atmosphere. Sometimes from the other way, I think, looking at the Earth.
I mean, anytime you want to send a signal through the atmosphere, you have to consider how is it being distorted by the atmosphere.
And it's not even just all the way to space. It's also just on the ground.
Yeah, it could be just between two locations on the ground.
And actually the turbulence on the ground is much more severe. Because also you have the atmosphere's thicker on the ground, and also you tend to travel, look pretty far distances on the ground. And because the ground's hot, there's a lot more turbulence on the ground because it sort of creates convection turbulence. And so even taking a picture that's something a few kilometers away, you could use adaptive optics like technologies. But I think, the military was really instrumental, I think, in advancing the whole field of adaptive optics. But it was really, as far as I know, the pyramid wavefront sensor was the first one that was sort of really built for astronomy, because it was more sensitive to atmospheric layers.
Okay. We had a little history lesson about the Shack-Hartmann wavefront sensor.
Okay.
When we did the lab here.
Yeah.
And it was kind of like a little bit of a coincidence where somebody, I might be wrong about this, but I'm pretty sure it was an astronomer who was doing some sort of like coronagraph-esque observation where he was covering up spots of the telescope, and then somebody else who was like, wait, I can use this as like a sampling of the light that's coming in
Oh yeah.
to see what the direction it's going in, or I guess you could say the gradient
Okay.
of the you can get a sampling of the gradient of the light that's coming in. And since then, I've always thought about why couldn't you just fit more lenslets into the Shack-Hartmann? Why do we have to resort to something like the pyramid wavefront sensor to get a better resolution?
I think it's sort of manufacturing, if I'm not mistaken. I mean, they do like the world of like sort of high resolution Shack-Hartmanns are sort of 20 by 20, I think, probably, which is 400 total.
Yeah.
Which is pretty good, but I think you run into basically a manufacturing problem, where essentially you have to have individual lenslets, right?
Yeah.
And then they have to focus onto a detector. But with the pyramid, it's kind of the opposite problem, where you have, as you grow the number of pixels on your camera.
Mm-hmm.
And I think it's just easier to have more pixels than it is to have more lenses.
Yeah.
Like, because they have to be physically made, as opposed to the pixels. I mean, we already have insanely high resolution cameras.
Mm-hmm.
In fact, the cameras we use for adaptive optics are, we use, in the tens by tens of pixels. Like we're not using megapixel cameras, the pixel density, actually we like big pixels. We don't even want small pixels. So in terms of like a growth thing from just a pure sort of manufacturing thing, the cameras are already high enough density. And and that's equivalent to having a Shack-Hartmann with more,
more like micro lenses.
More micro lenses, exactly. Yeah. But I mean, either way, I think it's less sensitive to the type of turbulence we see in the atmosphere than the pyramid. The pyramid was sort of designed with the idea.
What do you mean by that? The type of turbulence?
Well, the Earth's atmosphere isn't just like randomness.
Yeah.
There is like a profile that's well known. It follows a Kolmogorov profile. And so people studied the atmosphere, and they studied what kind of turbulence you have. And when we say like turbulence profile, it's essentially how much turbulence of what sort of size. You can imagine the atmosphere as being a bunch of like lenses stacked on top of each other, like tiny little lenses, and they have different sizes. Essentially, it's what mode the turbulence comes down as, right? And for instance, most of it is sort of large scale turbulence. So the predominant effect from the Earth's atmosphere is that something called tip and tilt, which is essentially just moves the spot on your camera plane. So that's the predominant effect, is just this sort of blurring motion. And then there's quite a bit of like defocus, focusing, so changing the focus position, astigmatism, a lot of these sort of lower order aberrations are much more common in the atmosphere. And really fine, detailed aberrations are much less common. And so when you design a wavefront sensor, you can, compute how sensitive that wavefront sensor is to those different types of turbulence, those different types of aberrations. And obviously, you want to choose one that matches the types of aberrations that you're expected to see.
Right.
And so it turns out that the Shack-Hartmann is not as good at correcting the type of turbulence that we'd see in the pyramid. However, it tends to be much simpler in a lot of ways. So it's been around for a long time, so they're pretty easy to make. I mean, you can make them in a university lab, like an undergraduate lab. You can make.
Really?
Yeah, I mean, there was the wavefront sensing lab you guys did. You basically made a Shaq Hartman.
Yeah. Well, the micro lens array was given to us.
Yes. I mean, like you can buy them off the shelf from.
Oh, really?
Yeah, I mean,
just like that.
You can just buy one. They're a fixed cost.
Are they expensive?
Not compared to a pyramid.
Yeah.
You can buy pyramid analogs. I don't think they're necessarily the most insanely expensive thing, but for getting a real like glass pyramid that has the optical properties that you could use in like a real system is quite expensive, I think.
So at the MMT, for example, why don't they put up the adaptive secondary and just close the loop on tip, tilt, focus, defocus, and just leave it on all the time?
Well, they kind of do in some sense. I mean, obviously, if they're going to use a different secondary mirror for different types of imaging, like they don't do wide field imaging or whatever, then they can't use that secondary mirror. Obviously, it's not there. It's like physically removed. But actually, for the lowest order aberrations on the mirror itself, they have what's called a hexapod, which is essentially a 6 degree of freedom mount that is adjustable. And so the first thing you do in an AO system is you just correct the lowest order things, which is tip, tilt, and focus. And you don't need a fancy wavefront sensor to measure those, especially like tip and tilt. You just kind of look at what position your star is in, and you just you design a control loop that keeps your star in the same position. Or we use the wavefront sensor for that. Because we have a wavefront sensor, but you don't necessarily need a fancy wavefront sensor for that. And then focus is similar. And so you just by using a mount, you don't need the deformable part of the mirror. Just by using a robust, a robotic mount, you can adjust for those in semi-real time. You can't get like super precise.
What do you mean by semi-real time?
On the order of like a couple seconds. So real time in the sense that like real time to humans, but like not real time to the atmospheric changes.
Okay.
When we say real time, we mean as fast as the atmosphere changes, as opposed to real time being, like many orders of magnitude slower. Like for instance, on the order of 5 seconds would be what I would say like semi-real time. But it's also sort of constantly being computed as well. So for the lowest order stuff, you can use a mount. But then it's really the higher order stuff. I mean, you won't get much of a good image. You'll just get an image that is centered. It still won't look super good.
So you were saying that, apart from this like wide field secondary that they have, that they do use with the non-adaptive secondary, they use the 6 degree of freedom mount to control for tip, tilt, and all this?
I believe so. I don't know if they do. They definitely do some amount of correction. I mean, even the primary mirror has some amount of correction it can do. Yeah, but it's manual. It's not like it's not real time.
Okay.
Like you can adjust for coma and stuff like that. I don't know. I don't think they do any.
Is that like bending the mirror?
No. I mean, the mirror is very. The primary mirror?
Yeah.
I think a little bit.
Cool.
It's either turning it to. I think on the back of it, there's some large sort of pistons that kind of move it a little bit.
Okay. So it's a little bit flexible.
I don't know. Actually, I think it's probably more just lateral movement than flexibility. Like sort of just moving it so that the optics are aligned.
Okay. Yeah.
I think it's more of an alignment thing than it is necessarily like. I don't think they have a super huge amount of flex on that. Yeah,
because it's glass. I saw how they made it.
It's big.
they like crush up a bunch of glass and then melt it in a rotating cylinder.
They cool it down for like a month.
Really? A month?
Yeah, it takes a long time to cool.
Wow.
Yeah, they cool it very slowly so that it doesn't crack.
So they can only do one at a time, and it takes.
They only do one at a time.
On the order of a month.
They're custom ordered, I think. Wow. They're making all 7 of the primaries for the Giant Magellan Telescope. That's what I think. That's kind of their full-time thing right now. I think is making those.
Yeah.
I saw one of them when I was there. I visited the Mirror Lab in Arizona. I got to see one of the mirrors.
Yeah, I walked by it. I didn't go inside, but
Right under the football stadium.
Yeah, right under the football stadium. Yeah. One thing that blows my mind is that these ELTs that are being built, extremely large telescopes, they were built with the idea in mind that they would be run using an adaptive optics system.
Yeah, all their secondaries are adaptive secondaries, as far as I know.
But they're all convex, right?
No,
Oh.
not all of them. The GMT one, I think GMT has one adaptive secondary for each one of its primary mirrors. So I think it has 7 total.
Wow.
Like it has 7 adaptive secondaries, and I think they are concave. The ELT one, I believe, is convex, and it's also segmented. Like none of the deformable mirrors are even one mirror, like the secondary deformable mirrors.
Because they're that big.
They're just too big. Yeah.
Yeah.
I mean, making any piece of glass that's contiguous that large, making a piece of glass that is contiguous and deformable that large, I don't know if that's. I don't know what the biggest one I know about is. Probably it's over a meter. I think they have a continuous one that's over a meter.
So the people who approved this project, did they know about the calibration problem?
Yes.
That was ahead of them?
Yeah, I think they have a lot of problems with ELTs in terms of like calibration, but they have been solved at VLT. The VLT is also a convex adaptive secondary, which is also run by the Europeans. It's a very large telescope as opposed to the extremely large telescope.
The next one will be tremendously large.
Ultra large telescope, yeah.
Is that a thing?
No.
Oh, okay.
No, not that I know.
That sounded real.
But at the VLT, they have similar calibration problems. I mean, nothing is as bad because, I mean, they have thousands of actuators, thousands of control degrees of freedom, and it's going to be tough. But they also, like, after they commissioned these telescopes, they discovered like new problems with like sort of the theoretical idea of AO at the scale with when you have segmented deformable secondaries, you end up with a problem called like pedalometry.
Yeah.
Which is this idea that like the different segments of your mirror are going to be relatively misaligned by exactly one wavelength. So you're only sensitive to phase to within one wave, and so if you have more than one wave of error but relative between segments, they'll be aligned to within one wave based on what
so they look the same essentially,
but they'll be exactly off by one wave exactly. So basically you can think of one as being whatever the wavelength of the light is away from the other one.
How severe of a problem is this?
I mean, it will destroy your imaging. Like,
really?
You won't see it on your wavefront sensor, which is the problem, but you will see it on your science image.
How come though? If it lines up just one wavelength off, how does that mess with your imaging?
Well, I mean, because it's just going to be a really bad aberration. I mean, it's essentially just an aberration.
Oh, right.
It's an invisible aberration only to your wavefront sensor.
Right.
But from any other perspective that's not the wavefront sensor, it's a very severe aberration.
Yeah.
And so this was after they sort of decided on the designs, I think. They ran simulations and sort of said, okay, this is a big problem. We're not going to be able to be sensitive to these petals. They call them petals because they look like a flower when you plot them in a certain way.
So there's 6 of these?
No, it depends on the mirror. I mean,
for the ELT.
I think they have 6 segments.
6.
That sounds about right.
Yeah.
And it only happens when your segments have like a big space in between them on your pupil plane. So it's a big problem because they have these big struts in the telescope that hold up the mirror because it's heavy.
Yeah, of course.
And so it has to be held up by these big struts, and they block some amount of light, and that basically creates the petal shape on the detector. And
do you know what like the obscuration would be?
I don't know what the obscuration fraction.
Yeah, like if you have like a 30-meter telescope, how big around is like
Do you need the struts?
No, not the struts, just the secondary itself. Like, how big is the secondary? Do you know?
Oh, it's gonna be in meters.
Really?
Yeah, it's gonna be big.
Wow.
It depends on your optical design. like the focal length, because like depending on the focal length of your system, it depends how far away you want the mirror.
Right.
I don't know if there's like necessarily a size you need, but you need it to be big enough that you can put all the actuators in, because each actuator takes up a certain amount of size.
Yeah.
And so if you have 3,000 actuators and they each take up a certain amount of area, you need a mirror that can fit them. There's a limited amount of density that you can do, and I think generally with a larger telescope, everything kind of scales up, and so it'll be quite large. I mean, it's big enough that they couldn't make it one piece.
Has there ever been like a secondary that broke because of actuators pressing too hard or moving in like a shape
there's
that
only
just
a handful of adaptive secondaries in the world.
Right, that's true.
And I think every one of them's taken pretty well taken care of, as far as I know. I mean, there has been the one that we're refurbishing. Like, I think the reason it broke was cooling liquid dripped onto the motherboards and fried the motherboards, and then they eventually ran out of replacements.
Yeah.
And so the idea with this one was to go without cooling. I mean, back in the day, they didn't have actuators that were they generated a lot more heat. They required more power. Nowadays, they're just better, so they don't need as much. They don't put off as much heat.
Yeah.
And so the idea was to be passively cooled, as opposed to actively cooled, because the cooling is what ended up actually breaking the mirror.
So passively, just as in like letting the environment,
the air cool it
down.
Yeah. Because I mean you're on a mountain, so it is pretty windy, especially on the tip of a mountain, and so you get a certain amount of, and it's cold too. It's usually just above freezing.
Yeah.
Critically, it can't go below freezing, otherwise things would would freeze. But it's usually I think like 40 Fahrenheit. 35 to 40 Fahrenheit up there. So things are pretty cool. And even though you have a bunch of heat being generated, you can cool it passively. That's the idea.
So is the heat being generated by the observatory itself an issue?
Not that I know of, except for the added turbulence. So anytime you have like a hot environment, especially next to a cold environment, you're going to get convection.
So that adds issues for the
the
observing itself.
It adds turbulence for sure. And so that is like a big issue. I think they call it like dome seeing. It's seeing related to the dome itself, seeing being what we call atmospheric turbulence. And so I mean the local environment in the dome, if it's too hot, that's going to create currents. But I mean, it's open to the air, so it's usually in the actual telescope room, it's usually pretty chilly. It's usually the same temperature as the outside. But most of the turbulence that you see is like close. It's what we call ground layer turbulence. It's sort of the turbulence basically right in front of the telescope. That's like about half of the turbulence in the atmosphere.
Wow.
Yeah.
Just right, maybe like 10 meters up.
Yeah, sort of in that regime.
Yeah.
Sort of they call it the ground layer. It's the layer that's like right at the ground.
So why don't you just like put the whole observatory 10 meters above the mountain or something?
Well, I mean, they go to higher mountains.
Right, but there's still going to be a ground layer, right? Or are there mountains that go above the ground layer?
I mean, it's just related to like the temperature of the actual Earth's surface.
Oh.
Yeah.
Okay.
But the main reason for going up on mountains, there's a few reasons, is because the ground layer you're above the majority of the ground layer.
Right.
You'll never get above the stuff that's like 10 kilometers up. But I mean that's why they go up on mountains, is because a lot of the atmospheric turbulence is on the ground, and that's why Mauna Kea in Hawaii has the nicest atmospheric conditions, because it's 14,000 feet or something like that.
Yeah. Does wind become an issue?
Wind is an issue for sure. There is a critical limit where you can't have your telescope running because
Really?
it's too windy.
Like, is this like a mechanical thing?
I mean, I think it's just the shake. Yeah.
Oh, okay.
Because I mean, telescopes are. I would say it's I mean, there's just things are up in the sky
Yeah.
on a mountain, and you have
Yeah.
20 km/h, 30 km/h winds.
Yeah.
Things are gonna shake around, and one of the big things about wind is actually the atmospheric turbulence is obviously highly related to the wind speed, because faster wind means the atmosphere is changing quicker. So you could have nights where the wind is not a problem, like maybe it's not you're not going to blow the telescope off, but still the wind speed is high, and so the atmospheric turbulence is very poor, and so you have bad conditions that night, and your adaptive optics system can't keep up. It's one of the reasons why having a faster system is better. But of course, for a faster system, you need typically a brighter star, because you're going to have less time to image. Each image of the star is going to
Right.
be.
So you have to be careful about how many photons you're not allowed, but are available
Yeah.
to be gathered.
Yeah, exactly. I mean, there's a lot of things to consider, but yeah, the number of photons that come to you from the star in a 1 millisecond image is going to be half as many photons as in a 2 millisecond image.
Yeah.
So if you want to run twice as fast, you have to do it with half as much light. And so, you can have a bigger telescope. That helps. So if your telescope is bigger, there's just more photons. It's larger collecting area. So there's more photons to collect.
Yeah.
Or you just run slower or faster. And so if the wind speed is really bad, and you're trying to observe something that's really faint, those are going to be tough conditions for an AO system. Whereas the opposite is also true. If there's a bright star and low wind conditions with low atmospheric turbulence that night, that's going to when your system is going to be most optimal.
Is there any reason why you would not use an AO system? Like, you would choose to not use it?
Yeah, there's a ton, and it's basically because the AO systems have limitations. If they had no limitations, then yeah, I mean, you would use it
Just
all the time.
always use it, yeah.
But the limitations come from their design. I mean, most systems are only for one star. So let's say you're trying to take a picture of a galaxy. Well, you need a star to observe the aberrations. So you use starlight to measure the aberrations in order to correct for them. So you need to have a star to observe, unless you have a laser, which is sort of you can use a laser to make a fake star. But in either case, you need some kind of physical star to actually measure. And if you're interested in observing a galaxy and there's no suitable star nearby, then it probably doesn't make sense to use an AO system. AO systems are also really expensive. So, your default really should not be to have an AO system, because it's just too expensive. And they are really complicated to use. They're not necessary. It's not really like press a button and just turn on the AO. Oh, look, it's better. Everything is better now.
You wouldn't have a research project
Yeah.
if that was the case.
Really, you have to start with your scientific goals, and you come up with, okay, this is what I want to observe. And then you decide, will adaptive optics help me reach that scientific goal? If you're trying to find, exoplanets, okay, by taking an image of an exoplanet, well, then AO is right for you.
Yeah.
But if you're, doing a galaxy survey, maybe it's not right for you. And so that's why, I mean, not every system has an AO system. They're just, but I mean, maybe in the future, I think the idea with a lot of our research is, okay, in the future, more people will use AO.
Yeah.
And especially with these like larger telescopes, that's one of the ideas behind them, is that, okay, you should always be using AO, or at least use it in more contexts than we do right now. And the only way that's going to happen is if we mature the technology, solve some of the problems that are very astronomy related, and just push the field forward.
So adaptive optics, the way it's done right now, is by a linear transformation of the wavefront sensor signal to a set of commands that are sent to the mirror. But the problem is quite non-linear, and so
It can be.
it can be,
It depends on your wavefront sensor.
right?
Some wavefront sensors are more linear than others. And I mean, maybe like a broad strokes thing is, okay, well, if it's non-linear, it's probably more sensitive. But then it's non-linear, and so it's not as easy to solve numerically.
Right. So are there any kind of new ideas in the field on how to solve these nonlinearities?
The main thing about the nonlinearities is that the pyramid wavefront sensor is the most common wavefront sensor in sort of modern astronomical settings. I would say overall in the field, Shack-Hartman is much more common. If you look at like sort of broad adaptive optics,
Yeah.
but in the context of like the astronomy community, pyramid wavefront sensors are sort of the new standard. And they have this problem with nonlinearity. And the easiest way I think about the nonlinearity is that the way the pyramid sensor works is that you push the light across all four of the facets of a optical pyramid, and it creates four images. And if the light is only in one of the four facets of the pyramid, then only one of the four images lights up. And the reason it's nonlinear is because if you're comparing the four images to each other and three of them are zero and one of them is, non-zero, then you have a nonlinear problem where you can make changes to the system, but you only see it in one of the four facets, for instance. And so for something to be linear, you have to see a smooth change. Sort of if I double this parameter, I get twice as much output. But if three of the four facets are giving you zero signal, you're in a regime where you have no information, and so it's highly nonlinear. And it's very easy for the system to get into that scenario. You just have to move it off of one of the facets of the pyramid, and the pyramid is very, very pointy, and so it's actually quite easy to move the laser or the starlight into one of the four facets without the other ones being illuminated.
So even just like the tip tilt, which causes translation in the star, that can cause the light to reach the nonlinear regime of the wavefront sensor.
Yeah, and it can do it, and it does it quite fast. But if you have very low turbulence, you're going to stay in a linear regime. The way that we mitigate this is by using something called modulation, which is essentially instead of putting the light through the tip of the pyramid, we rotate it very rapidly around each of the four faces of the pyramid, so that at all times light is in all four of the pyramid faces. And you have to put a huge tip to get this now circular illumination pattern away from the tip of the pyramid. You'd have to do a much larger motion. And so it's linear but less sensitive for a larger regime.
Okay, so hear me out. Why don't we combine the idea of a pyramid and a Shack-Hartman, where we have an array of micropyramids where you can always find illumination in some micro quadrant? Does that make sense? Does that make any sense at all?
Well, the first question I would have with that is, before it makes sense, I would have, is that even possible to fabricate?
Well, let's say it is possible. Right? Like instead of having just one pyramid, you just do because you said the tip is very pointy, so you have to be very specific with where you send the light. But if you just have smaller pyramids where it's just a bunch of tips in an array, then you're always hitting.
Well, the thing that I think with that is that the problem with that would be that each of the pyramids would be measuring a tip, right? But we already know how to measure. Like, the idea with the Shack-Hartman is that you break up the pupil into a variety of subpupils, and each pupil you measure just the tip and tilt. Because I think we said earlier that the tip and tilt is actually the easiest thing to measure. They don't even need the deformable mirror to do that. You can actually dynamically sort of correct for it just by watching the spot motion.
Right.
And so the idea with the Shack-Hartman is that, well, what if we just took the pupil of the telescope and broke it up into a bunch of different spots, and then just did the easy measurement of spot motion hundreds of times, Okay, and then that gives us our sort of more complex overall aberration measurement.
Yeah.
Now, if you put each one of those spot motions into a pyramid, all you would be doing is measuring, okay, you measure the spot motion just more sensitively, maybe.
Yeah.
Also, I mean, you would have like no photons because
You'd be splitting it up so much.
the reason why this sort of tip tilt spot motion is really easy to measure is because it's at the focal plane. So you're measuring it, you're measuring a focused beam, right? The pyramid measurement is done at the pupil plane, which is when you're taking up many, many pixels. You're looking at the whole pupil simultaneously, as opposed to a focused version of that. And so you could imagine that there would be less light in each one of the pupils because you're splitting it in 4. Whereas if you measure just the focal plane, it might be easier to measure. So I'm not sure it would work, even if you could do it that way. And I'm not sure you'd have enough photons.
Yeah. Just a spark of inspiration.
Yeah.
Because you said that, the pyramids are very pointy, so you have to be very specific. So I thought, maybe just like spam the whole field with a bunch of pyramids. But yeah. So the word on the street is that machine learning is going to be a little bit important in the world of adaptive optics.
Yeah, I think so. I think it's already become, every time you go to an adaptive optics conference, there are machine learning people there.
Yeah.
There's a bunch of different ways in which machine learning can improve adaptive optics. And it's not, for me, I've always thought that like the way machine learning interacts with adaptive optics is not the same way that machine learning interacts with like all the other stuff in my life,
Right.
I've seen machine learning algorithms, identify pictures of cats or people's faces. A lot of it's like identification, or these language models, classification, right? And it's doing things that like humans can do, but like just
a little bit automated.
You're just automating what humans can already do.
Yeah.
But with like adaptive optics, it's kind of different because I don't think like humans could do it.
Yeah.
Which is kind of interesting.
Yeah.
And also it's more just like nonlinear. It's real time as well. Whereas like a lot of the machine learning stuff, it's like not necessarily so real time. I mean, when I say real time, I mean like super fast. Millisecond, as opposed to like 1 second. And so I think it's an interesting place for machine learning to kind of solve problems. And solve problems that like I don't think that there's like, it's not just like, oh, humans can do this, but we don't have enough humans.
Yeah.
It's like the only way to solve this would be with a neural network.
Yeah.
Because it's really just about either nonlinear reconstruction or forward propagating something in time in like a non-linear kind of way that isn't super obvious.
Yeah. So let's say somebody comes in and starts calibrating their AO systems using neural networks. Do you think this is going to kind of overshadow all the other calibration techniques because it's so flexible?
I don't think neural networks will. I think they'll be mostly an enhancement to like some of the highest performing systems. I don't see them as being like required, because the thing about AO is that in like almost all contexts, the like linear approximation that we make about how AO systems work, we just repeatedly solve a linear system over and over again. It works really well in almost all contexts. Really, the neural network kind of stuff people are working on is for taking things to the next level, solving problems that are like, really only occur in sort of large scale, above 6 meter class astronomy telescope systems, which when you think about AO generally is not always like, it's pretty niche, but it's like, this is like the sort of highest octane AO systems that are out there. And I can totally see ways in which neural networks will improve the reconstruction modeling. So allowing us to use more nonlinear wavefront sensing methods. The big one that we work on here is predictive control, which is the idea of basically being able to account for the time delay that is taken to actually make the measurement. You can use neural networks to basically take your measurement and say, what would it look like in 1 millisecond's time, which would give you a more accurate representation of the current state of the atmosphere as opposed to the state of the atmosphere when you measured it, which was 1 millisecond ago because of the time it takes to actually do the measurement. There's a lot of like denoising in images and stuff like that, ways in which you can use neural networks to get sort of, you know, to understand like the noise properties of your camera and sort of try and improve the noise to get like a cleaner image. All those things, you know, can be done with neural networks without, you know, without huge advancements in machine learning. It's really just taking the technology and applying it to this particular use case. And, you know, the hardest part is actually getting it to work in real life. And one of the hardest parts is getting the neural network to actually run in under 1 millisecond, for instance. That's not always so easy to do.
Yeah. Have you ever heard of like a different type of wavefront sensor that is particularly nonlinear?
Oh yeah, for sure. I mean, there's a whole, people have like sort of formalized the idea of what are called Fourier filter wavefront sensors, which is this idea of like taking a focal plane and then applying a Fourier mask, which is sort of mathematically what the pyramid is doing. Pyramid is like a physical object, but sort of mathematically it's applying a Fourier filter to the focal plane. People have formalized this, and then they've come up with different filters you could use, and some of them are more nonlinear than others.
So what does a Fourier filter do?
Basically, you can think of like the focal plane and the pupil plane are related by a Fourier transform. Okay. That's kind of the relationship between the two. And so when you look at like a pyramid, you put the focal plane onto the tip of the pyramid, and then it produces 4 spots of the pupil plane, 4 images of the pupil plane. Now you can put a different filter in there. Like for instance, if you had like a 3-sided pyramid, it would produce 3 images of the pupil plane at the image plane. And a Fourier filter, I mean, is essentially just the sort of abstraction of that. It's what phase profile you put at the focal plane and on its way to the image plane. And people have found out that like one of the most sensitive ones is called a Zernike wavefront sensor, which I think is essentially just like a circular mask that is approximately the size of your focal spot. And those ones are, I think, optimally sensitive, but then they're also highly nonlinear. And so people tend to use them only for what's called like second stage AO systems. So you can like put an AO system in front of another AO system and then try and correct the residual turbulence. And so because they're nonlinear, the residual turbulence is obviously going to be much more linear than the initial turbulence, which is going to be highly, it's going to have a lot higher magnitude. And so the wavefront sensor is going to stay in a more linear regime if you only put into it the residual wavefront from another AO system.
So would it be more advantageous to pair neural networks with particularly nonlinear sensors?
I think so, yeah. I think that makes sense. Yeah, for sure. I think if you take a highly nonlinear wavefront sensor, you're obviously going to have more benefit compared to a linear approximation if you use a neural network. And so I think, yeah, there is definitely, I think there are people even doing this actually, where they came up with these sort of highly nonlinear wavefront sensors, and then they just use a neural network because it's not even clear they would work without one. Yeah, I also think in focal plane wavefront sensing is a good idea for this as well. In the there's obviously more light in the focal plane because it's focused. That's why they call it the focal plane.
Yeah.
Light's focused, so you can take easier measurements of it at the focal plane or close to the focal plane. So people will take images sort of just outside, so like slightly out of focus images. And you can, construct an algorithm that tries to figure out what the phase is given the focal plane images. and reconstruct it and then give it to your AO system. And I think a neural network would be a bit good at that. And I think people have done that, or they're trying to do that. Especially in there was a photonic lantern wavefront sensor people were working on that basically only is possible to work with a neural network because of how nonlinear it is.
Wow.
So I think the pyramid is really only the only reason you would really work on a pyramid for neural networks is because people use them.
Right.
Right, and they weren't designed with neural networks in mind. And I think if you were to like go back to the drawing board and design something where it would be the most optimally sensitive, assuming you could have a neural network reconstructor, I don't think you would do pyramid. I think you would do something more like these other options, like a focal plane or like a Zernike wavefront sensor. And people are definitely working on that, but to my knowledge, there isn't like some system out there that's just routinely using big neural networks and nonlinear reconstructors. Like this is all super new. And I think there's like definitely a path forward in trying to implement this at a telescope like MAPS or at another telescope.
So what would be kind of the advantage of using, let's say somebody comes up and says, I have a neural network that you can just stick onto your system and it, you just turn it on every night and it runs your calibration for the whole night automatically. What kind of like freedom would that give you?
Well, the neural network I don't think would like run the calibration. I mean, it would basically. It
would be the calibration, I guess.
It's the reconstructing. It would be the reconstructor, which is essentially like what you feed the wavefront measurements into. And you would still need a calibration. Depends how you train the network. Yeah.
The reason I said it would be the calibration is because it could just continuously learn the misregistrations in the system.
Yeah, it's possible if you have like there's like the policy optimization reinforcement learning thing that's out there nowadays, and it just says it always is trying to optimize the policy, and it kind of just learns everything. I think there is definitely some benefit to having a sort of a hybrid approach where you're not just giving a neural network like free rein to do complete exploration, because you do know a lot about the system, right? Like we do have, like in most cases, a fully operational system with a linear approximation of the wavefront sensor.
Yeah.
And like that's a lot of information that I think I would see a neural network sort of expanding on that as opposed to just like completely replacing it. Just because I think it might just be more efficient.
Yeah. I would think though that the network could kind of already encompass everything you know about the system already, and
I mean, it has to learn. There's a training stage at some point, right?
Yeah.
These things always have to learn, whether they learn in real time or they learn offline, or you do like half learning, half execution, or however you do it. Like you have to learn that information about the system. I would like to see a way in which it kind of already knows it. What I've seen with the policy optimization is it just defines. It's just maximizing performance, sort of blindly.
So how would you measure performance in this case?
There's a few ways. Depends on how fast you need to know. The main one is just what we call the Strehl ratio, which is just how star-like does your star look? Does it look like atmosphere or does it look like a star? And it's a ratio that basically is from 0 to 1, where 1 is it's perfectly diffraction limited, meaning that it's the absolute. You're limited only by the diffraction of light passing through the telescope aperture itself, whereas 0 is just you have no light at all. But that can take a little while to compute. It's not like you're not going to get that every millisecond. Whereas like a neural network might need some sort of feedback in real time. I don't know, depending on how it's doing its optimization. I would assume it needs it pretty fast because it's going to limit how fast it can change. And in that case, you typically just look at your residual slopes. So you look at how much atmosphere
is left over.
Roughly, based on what your wavefront sensor sees. that's typically how you would do it, or something similar to that. Yeah.
Yeah, this made me think of something we were doing where we would take the residual slopes and we would decompose them in terms of which modes are showing up in the residuals. This might be, more related to what we are actually doing. But the question I just thought of is, once we have an information about this, like the profile of the residual, would there be a way to kind of inform the system about this to say, here's where you're lacking and here's where you're doing well?
It's probably possible. I'm wondering if you just, because I don't know so much about reinforcement learning, like if you just give it a number or if you give it like a vector. In terms
I think it's
like,
pretty flexible in terms of what information you're trying to convey.
Yeah, I mean, the information in terms of reward, the problem with that is you just need to like average for a while. It's the same problem with the Stroll ratio, is that like, yeah, you can look at one, instance of the residuals and you could say, oh, look, there's, you have a lot of focus left over. Can you do better at that? But I mean, that's just one iteration, right? There's going to be a lot of randomness. It's going very fast, so things are going to change dynamically.
Right.
So you're going to want to, take an average over like a few seconds or however long it takes to build up enough signal to noise to get a really good idea, and then sort of tell it to do better at that. But I feel like that's probably not going to be fast enough feedback for it to like, I don't know.
Well, yeah. Any kind of information that you feed will be useful. It doesn't really matter how often. It'll just kind of limit the time scale, or the learning rate.
What I would feed it would just be a history of like the previous residuals. Like if you could just give it like the past 100 residuals.
Yeah.
The information would be in there, just wouldn't be like stacked up.
Yeah.
And so maybe it could.
Okay, but that would be more of like a digestion process for the network to do.
Yeah, maybe. Yeah. The nice thing about the using neural networks and adaptive optics is that we have a lot of information about the system coming in very fast.
Yeah.
We take a measurement of the
I love that.
once per millisecond, and we take a measurement very fast, and so you can do 1,000 iterations in 1 second, which the training, if you do sort of live training, it shouldn't take as long as it might take in other cases.
Networks love data,
exactly.
So
and you have infinite amount of data with this. And you have data coming in at different time scales as well. Like images of the star are going to be much slower time scales than images of the of the slopes themselves, or of the waveform.
Right, and that's one thing that I love about machine learning, is that you could be very creative. Humans think in a very, or I guess a more linear way, where it's like right now AO systems work as, okay, you have a sensor, you transform that signal into a set of commands, and that's all the information that your system needs. And a network is very indifferent to what you give it. So you could give it the slope measurements, as well as images of the star, as well as whatever else might be relevant, and it can combine all of these things in different hierarchical structures.
Yeah, it would be one thing that I haven't even considered is like, why don't you just have two wavefront sensors and have a network that gets information from two different wavefront sensors, like maybe a focal plane type thing and a pupil plane thing, and then it could
you could correlate information from both,
because they're going to be sensitive to different things. So certain wavefront sensors are sensitive to different modes, for instance.
What would a focal plane wavefront sensor be more sensitive to?
Well, I'd imagine it's most sensitive to tip tilt as well. Because, I mean, if it moves, I mean, that's the only one that you can really do by eye. I guess you can do focus as well. Kind of by eye, you can look at that and go, it's out of focus.
I feel like in this case, it would be better to have a focal plane wavefront sensor running in closed loop, because then you're kind of filtering out the lower order modes already.
Yeah, I'm not so sure. I mean, I think like I could imagine just a neural network reconstructor that just takes in a bunch of different types of information
Mm-hmm.
and is able to sort of do better than the sum of the parts kind of thing, where it can
Mm-hmm.
figure it out. Yeah, I don't think anyone's done that. I think the main reason no one looks into that is that you're splitting up your light into too many pieces.
Mm-hmm.
So every time you add a wavefront sensor, you add a thing, you have a
Yeah.
limited amount of light, right?
Yeah.
And it's not clear that you would get benefit from having two wavefront sensors. It's like kind of just like you only have enough light for one of them, so thinking about a second one is kind of ridiculous.
Yeah.
You want to make sure you put all your light into the one really sensitive wavefront sensor. So that's why I think no one's like even thought about it.
Mm.
It's the first time I've ever thought about it.
Yeah.
And but I think with neural networks, I mean, you could get more information from the focal and pupil plane simultaneously
Mm-hmm.
than what you might be able to do with sort of just a linear,
Mm-hmm.
because the relationship between the two, like you could have two linear systems, right? And the relationship between each of them is going to be not linear per se.
Mm-hmm.
And so I wonder if that's possible.
I also wonder if it would be possible to just feed some gigantic network just images of the PSF, tons and tons of images, and just see what happens.
Well, the one thing about focal plane wavefront sensing, which is the idea of, you know, using images of the point spread function of the PSF to figure out what the atmospheric changes need to be, is that there's like degeneracy. So, for instance, you can have an out of focus image can be out of focus in two ways, plus or minus focus. So you have your exact position of focus, and if you've ever like aligned a camera, you know, you're taking a photo of someone, they're in focus,
Yeah.
and you turn the camera, and they're out of focus. You turn the camera the other way, they're still out of focus.
Yeah.
It's actually not the way focus presents is the same, plus and minus a certain amount. There's a symmetry there.
Yeah.
And so just with one image of the focal plane, it's not even possible. Like there's a information problem,
Mm-hmm.
right? So you need, with focal plane wavefront sensing, you need a history to sort of kind of figure out like a history of your previous positions to know if you're like getting closer or further away from focus,
Yeah.
as you make corrections.
Mm.
So it's not just you know, using a gigantic network trained on PSF images like wouldn't work for that reason.
Mm-hmm.
Also, it has to be fast to execute, and like gigantic neural networks are going to be slower to execute unless you have,
Yeah.
I don't know, maybe you can use a bunch of GPUs put together or something like this. That don't really know about that, but
Yeah.
the idea is that like, yeah, I think with a relatively small network, you can make a significant improvement. I don't think you need to go with this sort of like deep learning, mega trained network kind of thing, because it has to be real time.
Yeah.
And you know, you're going to have so many different conditions. Each system is different. Yeah, there has been success with this policy optimization idea that someone has done, and that's pretty straightforward. So I don't think we need to necessarily make it more complicated. I would like to see a not sort of real-time reinforcement learning approach, like sort of more of a trained on simulations approach, where it's sort of like you unpack it from the simulations. It doesn't have to do any learning, and it works. That would be kind of cool. I think that would be a different approach that I think still has merit to it, because I think just doing broad reinforcement learning has its limitations.
Do you know some of the details about the policy optimization?
Well, as far as I understand, I mean, it's just basically policy optimization is a form of reinforcement learning, and it has like a very standard mathematical model, and someone has mathematically taken the framework of adaptive optics and you know, sort of analytically written it in terms of the policy optimization. There's like the environment and, you know, how you interact with the environment. All that stuff is sort of figured out in a sort of like semi-rigorous way. And then they've applied it to different bench systems, different sort of simulation systems, different systems that are test systems, and they're in the process of trying it on Sky. I think it can work. I think, you know, it's well on its way to working, I hope, but at the same time, I mean, you don't necessarily learn a lot about your system, because you just have this black box that is just, constantly learning, and that's your control system.
Yeah. Are they using the Strel ratio as the reward?
No, I think what they do is something like take the slopes and multiply them by the command matrix, and so they use like the next mirror command kind of thing, and they just feed it with a bunch of those. Something to that amount, and it starts off not being trained, so it starts off with a lot of randomness to it. One issue I think with that is trying to maintain the linearity, to try and explore while still being linear.
So is it actively trying to close the loop as it's exploring?
Yeah.
So how does it reach? How does it go from just a random set of weights to closing the loop?
Well, I mean, you can imagine that if it just learned the interaction matrix, it would be pretty close.
But does it have access to the mirror? Like, can it send its own commands to see?
Exactly.
What,
it does exploration. Yeah, there is an exploration phase or set of exploration in it where it is doing randomness and trying to learn about the system, and every time it does something, every time it performs a correction, it learns a little bit about this non-linear relationship between the hardware, and then over time it sort of becomes optimal the same way any policy optimization reinforcement learning does.
Is this similar to like a do crime method where it's just kind of exploring in a sense?
The do crime method is kind of analytically, it's like trying to back into the relationship. I mean, any interaction matrix thing is basically you put a shape on the mirror, you measure its response. Yeah. And if the response is hard to measure, you can do a correlation, try and weed out the noise, do a cross correlation. And that's what the do crime approach is. It does a cross correlation with, and to make the cross correlation better, it does random shapes as opposed to known shapes. Yeah. Just because the idea is that the cross correlation will be more efficient, because the randomness won't correlate with the atmospheric signal. Whereas like a mode, for instance, will correlate with atmospheric signal. Because
the atmosphere does present, some modes more than others.
Exactly. So the idea that's the idea behind that. In this case, it's just doing brute reinforcement learning. It's trying a bunch of stuff, and if stuff works, it moves in that direction in some space with a variety of different weights, and depending on which reinforcement learning model you choose and how you decide to update your policy, it's all that fun stuff.
So like, how much more research are you going to do before you start writing your thesis? Like, are you going to try to include some machine learning stuff into your work?
Well, I'm not an expert in machine learning, which is probably obvious.
Right.
Yeah. But I do facilitate machine learning experiments in adaptive optics. And so, that should be part of my thesis, is basically like how we implemented this into an adaptive optics system from the control perspective, as opposed to necessarily the details of the algorithm, the details of the architecture that we're using. Some of that will probably be in there, but not in the way that it would be in a computer science thesis, for instance. But I think I have, really there's the work on the predictive control networks, there's the work on the do crime calibration, and then supposedly I have to do some astronomy data analysis, which is
a little bit required.
It seems to be required. I mean, we'll see how, I guess when the push comes to shove, we'll see exactly how required it is, I guess. Maybe they'll let me graduate without it, maybe they won't. Really, as you get to the end of your PhD, you kind of just go like, I'm kind of done.
How do you get ready for a defense?
They won't let you do it unless you're ready. Oh. Really, that's
nice.
Yeah, you have a lot of people who will, tell you that you're ready. It's not really so much like, it's hard to get yourself in the scenario where you're just put on a defense and you're like, I don't know if I'm going to pass. Your supervisor should, prep you well for it. I mean, I'm not saying that is always the case, because, different departments work differently, but at least in this department, if you are put up for a defense, it's very likely that you'll pass. But it is very difficult to get to that position. You have to write it.
Yeah.
It has to be decent. People will have to read it and tell you that your thesis is good. You have to actually do the research before you can write it.
Which is most of the work.
Yes, that's years of the work.
Yeah.
You have every 6 months you have a meeting with your thesis advisory committee, and they will, be like, "Are you ready? Do you need an extra year? If there's funding issues, you would work them out. If you need an extra year or you need more funding or whatever." But yeah, I mean, it's very rare that you kind of just get put into a defense situation without like the possibility of passing, but so I mean, in some sense, it's like it's not a formality. I mean, obviously, people do like, you do get grilled for hours.
Yeah. How long?
It can be. I mean, there's 20 minutes public talk, and then.
What do you mean by public?
I mean, you give a talk, a 20-minute talk, and I think people are allowed to come. Yeah, like anybody can come. Depends on the department. It's pretty standard that like a lot of people will come in certain institutes sort of around the world. In ours, they tend to be fairly private. The sort of public talk section. Although I'm not actually sure if there's like a rule that it has to be private. I think people just culturally we don't have a lot of people showing up to them.
Have you attended?
I have never been to one. No, I've never been invited either. So.
Okay. I mean, you don't have to be. I guess.
I think most people. It's just them and the committee. And then you and your committee and your external people will grill you for probably at least an hour. I've heard several hours before. They ask you questions from all around, anything that would be related to your research.
Yeah. And are you talking to experts in your field or just like experts in astro in general?
Depends. There is at least always one expert in your field. So there's your supervisor, who is almost certainly an expert in your field, and they'll do some grilling. Your supervisor doesn't just give you the softballs, like. And then there's your rest of your thesis committee, which are typically professors in your department who are as close as possible to your field. So, in my case, there's instrument people on there. And then you have two externals. There's like an internal external and an external external. Internal external is like somebody who's in the university but is not in your committee and has never had a paper with you or anything like that. But should also be, a subject matter expert. And depending on how niche you are, they might be very loosely a subject matter expert. And then the external is, as far as I understand it, one of the most important people. In my case, for instance, we've already chosen who it's going to be.
Already this far out?
Yeah, like a year out. You start to think about that, yeah.
Do you get to choose yourself?
Usually you and your supervisor will. There's usually not so many people it could be. It's actually a lot more, because like it's going to be a subject matter expert.
Does it have to be somebody in the department?
No, it can't be someone in the
department. It can't.
They can't be at the university, I think.
Oh.
Actually, I'm not sure if they can't be at the university, but like they have to be like, you could never have been on a paper with them, and your supervisor can never have been on a paper with them. There's like some rules like that. I'll learn more about the exact wording of it, but it's supposed to be someone in the field who is like relatively well respected, hopefully, and is capable of really grilling you, and also is capable of evaluating your contributions, but has no bias towards you. That's the idea. And so for us, it'll be, I think there's like some AO experts in the UK that we're looking at trying that, we don't know them, which is kind of the point.
Yeah.
And I've heard stories of people as externals, like giving them an insane amount of comments because they would have never interacted with your thesis before, and they'll have a bunch of things to say about it, ideally.
Yeah.
Well, I don't know if that's ideal, but.
Yeah. Could it be somebody who's, in geology? Or it's just something completely unrelated?
I don't think so. I mean, not that I've heard of. If it's possible, that's definitely not the norm. I mean, like we're looking at, someone who's very experienced in AO specifically, and someone who's doing, as close to what I'm doing, but doesn't know me. or maybe they know of me but they don't know me like personally.
Yeah.
They're not biased towards me. That's
Yeah.
what we're looking at. I think that's pretty standard. I mean, like I said, I mean, everyone's programs are different, but I think the idea with an external is like they're supposed to be, they're what is preventing the university from just giving degrees to anybody.
Yeah.
Right. That's like their role is to audit the university's sort of like, that someone else other than just people in Toronto think that you are a PhD level academic.
So does it come down to a vote, or do they just agree?
I think it's a vote.
Really? Wow.
I think it's like a consensus.
Wow. Okay.
I think it's like a.
Oh, so if one person doesn't want to,
I don't know
it's
about
just a veto.
I don't know. I don't know if it's like a jury or if it's like.
I'd be interested
My
to find out.
understanding is that it's good. My understanding is that it's like, like a consensus. Like,
Yeah.
And there are like conditions to passing and things like this where like you have to like put comments on your papers, and that can take like a year of like.
Really?
And
Wow.
there's like all these like rules about when you submit it and when you send it to people. It's actually like a very formal process, more formal than like a lot of the other stuff we do at the university. Like you have to actually like send it to them at a certain number of days before the defense. They have to have a certain number of like this. I mean, all that kind of stuff. So yeah, I mean, it's not an easy process by any means, but like, I don't think that you get there on the day and you're just like, oh my God,
Maybe.
I have to defend my thesis.
Yeah.
I have no idea how to do it.
Yeah. Are you thinking about staying in AO after you graduate?
I'm thinking really hard about it. It's a tough decision because
Maybe an underappreciated field.
I think all of academia is like financially underappreciated.
Yeah.
And that's a big factor. I mean, that's something that like you have to, at some point in your life, you have to be like, like they don't pay you a lot to be an academic. And a lot of the times, like it's not, it's not like financially the best thing you can do. And in some cases, like you can be fairly bad off in academics, especially in like a lot of the positions I was looking for in Europe were not paid very well. They have very different, cost of living and stuff there as well. So, there's a lot to consider. But like a lot of it's immigration. Like you have to move. If you want to be an academic, like you're moving across the world. Like,
do they pay for a relocation?
Sometimes I think so.
Okay.
Yeah.
Okay. Good.
Sometimes,
Good.
depending on your university, and it's like, do you really want to like, oftentimes you'll be immigrating, especially to the U.S., going through U.S. immigration, just to get paid like much less than you would if you were to leave, right? So you're taking on less money with more hardships, but the idea, I guess, is that there's like prestige.
Yeah.
But I don't know.
Or maybe future prospects.
But
yeah.
Honestly, if you have a PhD in like a instrumentation related field, you're very close to engineering.
Yeah.
And if you're going to try and start a family, you want to stay in Canada, it's a tough decision, and it's a decision that like I see a lot of astronomers make where they don't stay in astronomy. It doesn't have a super high retention rate depending on what university you go to. And
yeah, I mean, especially because the skills that you gain are super applicable and for other positions.
Exactly.
It's very easy to just say, you know what, like I'll go run some NumPy stuff for some insurance company.
You gain a lot of transferable skills, and it's a very small field. Like people maybe don't understand how small it is relative to like biology type fields are much larger. They have many more positions, and so astronomy can be very competitive. It can be very niche, and you're also learning a bunch of transferable skills that have higher financial incentives for you to leave.
Yeah.
Especially when you get to like the PhD level, and then it's like the only reason you would stay is if you like really love it, which a lot of us do. Like definitely, I love my job. And I think a lot of us really love doing astronomy, but like, it's not like, oh, you just,
Yeah.
I just continue on in AO. It's like super easy, and it's like you have to apply for these, insanely competitive jobs for, financially less than you would get in engineering. Like entry level engineering salary is much higher, or definitely higher than what you get, especially in the U.S. So I'm thinking about it. I'm thinking about applying to these jobs and moving and everything like that. But I'm also thinking about whether that's worth it for me.
Yeah. I mean, you'd be stuck on kind of this set track, right? If you decide to stay in academia.
Yeah, and the longer you're in academia, the more it's like, do I really want to because it's not like you leave academia and you get a position at an engineering firm. You start at the beginning.
Yeah.
You start early, you become an early career professional again. And so, yeah, especially after a PhD, that's one of the big drop-offs in terms of people who stick around. But I don't know, there's some appeal to it. I mean, it's interesting work. And that's, I think, the most important is it's interesting work with relatively flexible time commitments, and you get to travel a lot to fairly remote places to go to telescopes and work on systems like that, and it's kind of cool.
What would be some advice that you have for first year students who are kind of fantasizing this idea of being this genius physicist, working with Albert Einstein, thinking that this is the life that they want? When I remember when I was in first year, this is not exactly what it turns out to be.
Yeah, the number one thing is that when you're young in physics, you're mostly learning theoretical physics, and the reality is that the reason theoretical physics exists is because there's the messy world of real physics where people are building stuff, they're doing experiments, they're crunching numbers, they're doing a lot of computer programming, and it's not just people sitting around at a chalkboard. I mean, there are people who sit around at a chalkboard, but those people are not necessarily the majority. And that's the reality of it. And the thing that I would recommend is to learn programming early, often, and well.
That is very good advice.
Learn it from people who are experts in programming and not people who are experts in physics, because people who are experts in physics are not experts in programming.
Yes.
And every opportunity you have, that's my number one career advice for young people is to get into programming, just because that's what everyone does in the real world these days and it's a very transferable skill. And the other advice I have is to look for research opportunities. It's not necessarily super easy to get research opportunities these days, or sort of generally. So if you do happen to get some sort of research opportunity, just my advice is always just to show up every day. The more you can physically, or I guess nowadays with Zoom, this is pretty popular, but the more people know who you are, and they're gonna probably try and help you and give you letters of recommendation and things like that. For me, that was my number one career start, was just that I showed up more than the people who I was in this sort of volunteer program with. I just kind of kept showing up and got to know the people, and a lot of it is social networking stuff at the early stages, trying to have people know who you are, and sort of that's kind of can be as important as the actual academics of it, is just having good relationships with your professors and mentors.
How do you find a good mentor as a young student?
Oh, I wish I could.
Yeah.
I wish I knew the answer to that. I mean,
did you have one?
Yeah, I mean, the way for me, it was just going. I think Keith was a big mentor to me as a professor. He was just a really, I just sort of stuck around his office, kind of bugged him, I guess, answered emails, wrote him emails, because I found this program through the Facebook ad, and that was really what got me a mentor. But I feel there's other opportunities, whenever I've done mentoring, it's always been through a program, which I think is probably more common, is that people join a graduate student mentorship program, or they go to their professor's office hours.
Yeah.
or the TA's office hours, and they just like, show up, ask questions, be engaged, and then they sort of get sort of mentorship from that.
Yeah.
But in terms of like official mentorship, you can get a lot from programs that are run by your department. We have like several mentorship programs here that we run from like undergrad to grad student, between grad student to postdoc, mentorship, stuff like that. And it can definitely help for sure.
Yeah. I didn't have one myself. I think I started filling out the application because there's also one with the arts and science department. And I just never followed through. It almost seems like, when you're a student signing up for all of these, because it's not just like signing up for a mentorship program, you're also signing up for different clubs and committing yourself to different activities. It just feels like kind of one more responsibility that you're adding on top of the pile, the existing pile. So
I mean, students are really overworked.
Yeah.
Like, especially like students I've talked to, I mean, like, yeah, they work a lot, and I don't know if there's ever really a solution to it. I mean, I wish I had a solution to it.
Yeah.
I see a lot of overworked students, and I don't know.
Did you feel overworked as a student?
100%.
Yeah.
Yeah, I felt overworked. I don't know how I managed it. When I look back on all the things I was doing as a student, I have no idea where I found that energy from.
Yeah.
Where I had that, like, I don't know. I had just insane amounts of like overconfidence, which was probably
a good thing.
Probably a good thing in the end. But
what do you think your hardest semester was?
Like academically,
Yeah.
or like emotionally, because like I would say the emotional side effects of like being that overworked is probably more significant than the like academic work. I feel like the work gets harder in fourth year, but like
Really?
yeah, I found it got a lot harder like conceptually.
Right.
There was probably a time in third year when I had the most like number of hours of work, especially when I was doing like labs, like astro labs took a lot of work.
Yeah.
And a lot of time, and
For sure.
doing that with like all the other courses
Yeah.
you're taking at any given time.
Yeah. In my first semester of third year, I was doing second year physics labs at the same time as third year astro labs.
Yeah, I did the same.
I was writing reports
Yeah.
all week long.
Yeah.
It was crazy.
I mean, I would routinely stay up like way too late. Like I had a lot of sleeping. Like one of the worst things about being a student is that your classes start at like different times in the morning.
Yeah.
Which is like something that like it's one thing if you have a schedule where like every day at 9 o'clock you come in and like, you get used to it and you find a rhythm. But like when you can sleep until noon and then 9, 11, and then 10, and then and this and that, then you start like your sleep pattern gets really wacky.
Yeah.
You start staying up late, like working on assignments. That was always what I was doing.
I would definitely write it up to the first class of the day. Just wake up whenever you can.
Exactly. Which was like super unhealthy. And I think like I'm not surprised there's so much like burnout in students. The workload can be like super high, definitely higher than in grad school, which I think most surprises most people because you do hear a lot of stories of like grad students being overworked, but like
I think it's also a population thing where there's just maybe because there are more undergrad students, even though it might be like the same percentage, just quantity wise, some people just aren't ready for that, and so just a lot of people who just, like raise their voices and say, you know what, this is a little bit too much.
Yeah, I felt undergrad to be very demanding work-wise.
More stressful?
Yes, more stressful for sure. More stressful, and like everything was. Yeah, I mean, there was no breaks.
Yeah.
Like in grad school, you get maybe less days off because technically you get the whole summer off. But that's not really true. I mean, you work in the summer usually. But you instead you have the choice about when you take the time off, which is super important. Like if you had family events and like Thanksgiving and this kind of stuff in undergrad, it was like can't go to that.
Yeah, literally.
I have 1 week a year I can go.
Yeah.
And like as an adult doing that, where you have like 1 week a year that you can like
that you can't choose.
That you can't choose when it happens, and that's when you have to do stuff. Like it's really like sort of for like building a habits and long-term health, it's like not super nice. And then during the time you're actually working, I mean, you're working like very odd, long hours at odd times is usually not a good mix.
Yeah, and it's also different classes have different frequencies, and so sometimes it's all constructive in one part of the year and spread out in other times. So
Yeah, it's really hard to keep track of.
yeah.
But in grad school, I mean, you get like, at least for me, it's very much more like a 9 to 5 kind of environment, even though it, obviously probably more like 10 to 6 is probably more common. And yeah, I mean, you can take time off when you need it. You know, you get paid, which is nice.
Yeah.
You don't get paid a super large amount, but you still get paid.
Yeah.
And you know, TAing is like, in my experience, TAing has never been an overwhelming amount of work. And you know, people have always understood if you have to TA instead of like doing your research, etc. So
Yeah. Well, cool. I guess we've been going on for over 2 hours. This is a good time to cut it off. Thank you for coming on to the podcast today.
No
It was
problem.
great having you. I learned a lot about adaptive optics, and I work in adaptive optics. So
I'm still learning about it like every day. So
yeah,
there's always more to learn.
I guess a fair warning to the listeners would be to listen to the previous episode I did on adaptive optics, where I kind of spoke about wavefront sensors and wavefront correctors. That would be kind of a good little intro. Yeah, other than that, I hope everybody enjoyed this episode. And yeah, see you next time.